Thank you very much. Thank you for the invitation. So, this talk is about compressible fluid dynamics. It's not about shape analysis, but the tools that I will present can be in principle applied to variational problems on diffeomorphism groups from the numerical point of view. So what I will show, in fact, is a numerical discretization of compressible fluid equations that is realized in a geometric preserving way. So this is a joint work with Werner Bauer, my former postdoc, who is now at Imperial College, and it's based on some recent papers that we have together. So as I said, it will be about fluid, but the geometric tools that I will discretize or I will use are also appearing in some various approach of shape analysis. So, but my goal here is to discretize in a structure preserving way some classes of PDEs that arise in dynamics of atmosphere and ocean. So these are PDEs, and if I compare them to PDEs of compressible fluid dynamics, they have several particular features, like this 4-1 here. For example, about the length scale, right? The horizontal length scales are much larger than the vertical ones, and there are two physical effects that are very important in these fluids. This is the stratification, right, due to the gravitation, and the Earth rotation. So, based on these important characteristics of these equations for fluid dynamics, people have realized several approximations of the initial fluid equations. So the initial ones are these ones. These are the ones for a compressible fluid, right, with velocity v, subject to rotation here. This is the angular velocity of the Earth, and stratification here, realized by the gravitational force, g times the vertical vector. And you recognize here the pressure, right, which depends on the mass density and the entropy. The equation for the mass density is here, and we replace the equation of the entropy by the equation for the potential temperature. I will explain a little bit later what is this variable. But so from these so-called primitive equations, several approximations are derived, right, like these 4 ones here. And as I said, I'm recently interested in this kind of PDEs, and this kind of discretizations, but as I said, this talk also provides some foundations for discretizing problems on diffeomorphism groups. Okay, so let me first recall some properties of the equations in GFD dynamics that are useful for my approach. So first, all these equations have a Hamiltonian and Lagrangian formulation. So Hamiltonians mean they preserve some structure. Lagrangian means that they have some variational principle behind them. And the various equations that I mentioned here also arise from variational principles, but applied to an approximate Lagrangian. And more importantly, many of the conservation laws that are useful to understand these models arise again from geometry. For example, the famous Kelvin circulation theorems, or the conservation of potential vorticity. Already here you see that these two conservation laws have completely different origins. The first one is due to a symmetry of the problem, and the second one is a Casimir of the Hamiltonian structure. So one is due to the symmetry, and the other one is due to the geometric property of the underlying geometric properties of the equation. Also for us, we are more interested in having a good global behavior rather than a high precise behavior in local. So because of all these reasons, right, I will propose to use variational integrators to discretize these problems, and you will see that all these properties that I mentioned here can be also formulated in a discrete setting. So they will have some discrete counterpart. So this is the plan of my talk. So first I will briefly recall what is done when we discretize the problem in time only, right? Discrete Lagrangian mechanics, no continuum. Then I will recall the variational principle underlying this kind of equations, right? This is the main step, the discretization of the configuration space of compressible fluid dynamics by preserving the geometric properties, or here the Lie group properties of this configuration space. Then I will proceed further with more particular aspects. So let me start with discrete Lagrangian mechanics. So all the problems that I will present are issued from Hamilton's principle. So it's useful to have a quick look on it. So in Lagrangian mechanics, if you have configuration manifold Q, in our case it will be a Lie group, and you have a Lagrangian depending on the position and the velocity. In absence of irreversible process, the dynamics of your system is given by the Euler-Lagrange equations, which are describing critical points of this action function. Now there is a discrete counterpart of this, a discrete in time counterpart of that is useful to produce numerical schemes for these Euler-Lagrange equations. So this is by now a very well developed subject. You have here some important reference. But the basic idea is not to discretize these equations, but the Lagrangian. So this Lagrangian is discretized in a Lagrangian LD, and your tangent bundle TQ is discretized as Q times Q, which corresponds to initial and final configuration of your system at consecutive time steps. So for example, if you choose a time step delta t, and you have 2 points qk plus 1, you construct a discrete Lagrangian, which is an approximation of the action functional here between 2 consecutive steps, right? And then you take variations of these action functional in the discrete sense, and you get a numerical scheme for these equations here, which are called the discrete Euler-Lagrange equations. So this is the easy part of the discretization, because it's only concerned temporal discretization. So the discrete flow associated to this scheme has several interesting properties. First, it inherits the symplecticity of the flow of the continuous Euler-Lagrange equations, right? In the case when the Lagrangian is regular. So it preserves a symplectic form. This symplectic form is given in terms of the discrete Lagrangian by this equation here. So it's a discrete 2 form on Q times Q. And you see that it's symplectic if and only if the discrete Lagrangian is regular. So more than that, more than being symplectic, this flow also preserves the Noether theorems. So if you start with a problem in mechanics in which you have some symmetry in the Lagrangian, and if you are able to insert these symmetries, or to preserve these symmetries also for the discrete Lagrangian, then the discrete solution of your scheme will automatically also inherit some discrete Noether theorems. Now, due to the symplecticity of the flow, it also exhibits a very nice energy behavior. This is a well-known result from symplectic, from backward error analysis, which tells me that the numerical schemes, in fact, preserve an approximate Hamiltonian with respect to the problem that we discretize. So this is by now well developed. There are a lot of extensions of these preliminary ideas. And let me mention, for example, that we know how to treat non-harmonic problems, non-smooth systems, and also space-time problems by doing temporal and spatial variation, discretization in the same time. This is not what I will present today. Today I will present first a discretization in space of my problem, and then apply a discretization in time. This is not always well suited, but this is where we are so far with the fluid equation. So coming back to the problem that we consider in this talk, there has been a lot of effort to try to discretize equation of geophysical fluid dynamics in a by preserving as much as possible the energy, for example, or the Casimir. You have here a list of works, but there are much more. And so our problem attack this issue, but from a pure geometric point of view. So here I'm starting by recalling the geometry of continuum mechanics in the smooth case and in the reversible case. So for compressible fluid, the manifold that I start with is a diffeomorphism group of the fluid domain. And if this is incompressible, of course, we impose the diffeomorphism to preserve the volume form. And here I work with a compact manifold with smooth boundary, orientable. And in this talk, I will need to ignore all the analytic aspect of this approach, because I will, for time reason, but it's also important to have this been done properly in the language of infinite dimensional manifolds. So I will work in some way in a formal sense here. So the motion of fluid is given by a curve in my diffeomorphism groups. We have seen this map phi earlier. It was denoted chi. And the Lagrangian of fluid dynamics is also defined on a tangent bundle, the tangent bundle of the diffeomorphism group. And the equations in Lagrangian representation are also given by Hamilton's principle, right? And at this point, your variables are a diffeomorphism and its associated velocity. And you impose that your action functional is critical with respect to arbitrary variations of your fluid motion. In addition to this, you have also, depending on the theory that you are considering, to consider several tensor fields that are located on the reference configuration, which I denote by large X. Here the mass density, the entropy, and the potential temperature. Okay, so in the Lagrangian description, my variational principle is extremely simple. It's just Hamilton's principle. Now, what about the spatial or Eulerian description? So, if we look now on Eulerian domain, small x, we define the variables, all of them, with respect to the flow, using this geometric operation. Here, it's simply saying that phi becomes the flow of V. And here, we push forward the tensor field that I mentioned earlier. So earlier they were just fixed quantities, right? No time dependence. And when I look at them in the Eulerian frame, they acquire some dynamics due to the time dependence of phi, right? So rewriting the Lagrangian in terms of Eulerian coordinates, you get this expression. You have here the kinetic energy of the compressible fluid, the mass density, and here the internal energy, right? You can think, for example, of a perfect gas, but any here state equation can be inserted. And I work here with the entropy density, not the specific entropy. So now the idea is the question is how to write Hamilton's principle in Eulerian variables. So how to write this in Eulerian variables? So you have to take variations of these Eulerian fields, but only those that are induced by variations of your Lagrangian field, right, phi. So it's a little bit of computation to get the answer, and you get this type of expression here where zeta is a free vector field. So for example here, the variations that you can take have this form where zeta is any time dependent vector field, but even if you choose here any dependent vector field, this doesn't mean that the result is arbitrary. So this is some constraint on the variation. Similarly on the mass density and the entropy. You can also approach this by using Euler-Poincaré reduction on Lie groups. This is a very efficient approach that has been described in this paper. So you get this PDE for compressible fluid dynamics. So here dLdV is the fluid momentum. It's a one-form density. This is the Lie derivative of our one-form density. And these are ordinary differential. And you have here the transport equations for ρ and S. Okay. So how shall we discretize this picture now? So the first step is evidently to discretize in space the configuration space, so the diffeomorphism groups. So we will replace this infinite dimensional Lie group by a finite dimensional Lie group, right? A well-chosen approximation, but we want that this approach works for any domain of the fluid. For example, we are interested in the sphere because of atmospheric science, and we also want to be able to do some refinements, so to treat unstructured mesh. Then once this is done, we can repeat this variational process on this finite dimensional Lie group and get a spatial discretization of our problem. Later we can discretize in time by using the discrete Lagrangian mechanics that I mentioned earlier. So this first idea has been developed in this paper for the incompressible case. It has been then extended to several models by including rotation, stratification, etc. So what I will present today is the last extension, which considers the case of compressible equations. So as I said, here I'm interested in fluid, but if you have variational problems on diffeomorphism groups, and you think that it would be important for your problem to do the discretization in a geometric way, this is one way to go. So let's review the incompressible case. So it's a kind of a hard task, right? If you have a group of diffeomorphisms, to find a good finite dimensional approximation. So what they did in this initial paper, they looked for a group action on discrete function that preserves some of the property of the initial diffeomorphism groups. So this group, since this is incompressible, preserve the L2 inner product and also preserve constants, right, by acting on the right. Here I'm considering the action of diffeomorphism group on the right on functions on the domain. Like, for example, you can think at the specific entropy. The evolution of it is given by acting on the right by the evolution diffeomorphism. And the idea is to try to imitate this in a discrete level. So don't discretize the diffeomorphism group first, discretize this space. So several choices are possible. We choose to discretize them only by attributing one value per cell in your chosen mesh discretization. And then you want action of a matrix group on this vector that preserve this. So you have to first say what kind of L2 inner product you consider on this. Is simply the inner product of F and G weighted by the volume of each of the cell of your fluid domain, right? So you get this inner product. So the picture you have to have in mind is the following. In the continuous case, the diffeomorphism act on the right by composition. In the discrete case, your matrix group, that I denote this way, act on the left by ordinary multiplication on vectors. So from these two conditions, we get these two conditions. So Q is an n times n matrix, and we impose that it acts on n vectors in a way that preserves the L2 product, so we have this condition, and also that it preserves constant, so we have this condition. The sum of all the columns are 1. So you get this finite dimensional Lie group. This is the discrete incompressible diffeomorphism. So we have seen that in the Eulerian description we will work on the Lie algebra of this Lie group. So we compute here this Lie algebra. And now there is a little bit of work to relate these Lie algebras with the original velocity of the fluid, right? So it's a little bit of work, but at the end, what you observe is that the matrix element of A, your discrete vector field, corresponds to the flux of your continuous vector field through the phase common to the cell I and J divided by the volume of this cell, right? So this is a important step because it means, among other things, that the matrix element Aij, if Ij are not neighboring cells, must be 0. For example, there is no flux from this cell to another cell at the other extremity of the mesh, right? So from the point of view of geometry, this means that we have a non-holonomic constraint because not all the Lie algebra element corresponds to physical velocities. But for us, it's no problem. We know how to treat non-holonomic constraint in the variational principle. So we apply non-holonomic Euler-Poincaré reduction. So if I come back, what I am doing here, I'm having some expression of the discrete Lagrangian on the Lie algebra, and I'm repeating this computation in the spatial discrete level. So I'm doing exactly this and this, but on this Lie algebra. And what I get is this. So here you recognize the same expression for the variations as before, but in non-holonomic mechanics is known that to treat this problem we have to take this C here, which corresponds to the zeta earlier. It has to satisfy the same constraint as the one we imposed on the velocity. So you get this abstract equation here. So here dl dA is the partial derivative. This is the Lie bracket in the Lie algebra. And omega is the matrix of all the volumes of the mesh discretization. So more explicitly, you get this form. So this seems a little bit abstract, but this is a spatial discretization of the Euler equations for fluid dynamics on any mesh of the fluid domain. But I didn't yet specify the Lagrangian. That's why you still have these partial derivatives here. Now, how can we pass to the compressible case? So it seems very easy, right? You simply remove the incompressible condition. So that's what we do first. So our larger group is just GLN plus, in which the column of the matrix are 1. The sum of the column of the matrix are 1. So you get an n square minus 1 dimensional Lie group. The Lie algebra can be easily computed, but here again, we take the same L2 inner product as before, and we compute appropriate dual space for this. So a dual space is given by these vector space here, where Kii is 0 for all I. Right? This is one possible choice for this dual space. and this is the one that we shall choose for the discrete momentum of the fluid, discrete momenta. So this is the easy part. Now we repeat a little bit the argument that we did before to relate the continuous velocity with the discrete ones, and we discover the same relation as before, of course, for I and j, but now there is some a I that were 0 earlier, right? It corresponds to the integral of the divergence of V on the cell number I. So at this point, we observe that this yields a new non-harmonic constraint, right? So we removed the incompressibility constraint from earlier, but removing this introduced a new difficulty that was not present in the incompressible case, which basically says that the Lie group is too big and that we have to impose an additional constraint. This constraint is the following. So A transpose omega plus omega A is no more 0. This would be an integrable constraint, but it's a diagonal. And you can readily check that this is non-integrable, right? The Lie bracket of two guys like that is not necessarily of this form. So having this described the distribution, now we have to compute the space of momenta in which the discrete fluid equation will live. So it's the dual space to the Lie algebra quotiented by the annihilator of this distribution, right? We are looking for a space in non-degenerate duality with this space, right? And the answer is this. So this is a good surprise, because this space here is equal to discrete one form. So I will not here mention a lot of tools from discrete exterior calculus, but this is a well-developed subject, and it was a very good surprise for us to realize that this larger Lie algebra, finally, when it is quotiented by the annihilator of the constraint, recover discrete one forms. And we will need this projector when we compute the Euler-Poincaré equations, which tells me how to project a momenta that is not orthogonal to R to a one that is. So you basically do this operation here. Okay. So far we have discretized the group. We have seen the constraint induced by velocities, by the fact that these A have to be discrete version of velocities. It remains to see how this group act on densities. So from construction we know that how this group act on functions. So from our point of view, acting on density is not that hard. It's just taking the dual action with respect to the correct duality pairing and the correct space, and we get this formula here for acting on density. So this is a discrete diffeomorphism acting on a discrete density. It's just one value per cell of the mesh, right? So it's not Q times D, it's this combination here, which involves, of course, the contribution of the volume of the mesh discretization. As it should, it's a kind of analog of the Jacobian here. And the Lie algebra action can be computed simply by taking the derivative. So we get this principle here again, which is the discrete version of the Euler-Poincaré principle that I mentioned earlier. So A is a discrete velocity, D is a discrete density, and these are the variations that I'm allowed to take. If I were working in Hamilton's, in the Lagrangian picture, I would use Hamilton's principle, more precisely Lagrange d'Alembert, and I wouldn't need this constraint on the variations. But my method is really Eulerian, so I need to consider them. So with a little bit of work, we can formulate an abstract equation. Soon you will see concrete schemes, don't worry. So this is still abstract at this point. So how do we obtain this? We take variations, we integrate by part, we obtain some expression here. This corresponds ultimately to the convection term, and this is the right-hand side term that corresponds to the pressure, etc. And once you have this, you have to remember from this lemma here that you need to project down to discrete one form. So this is what this P is doing here, right? And you abstract a spatial discretization. I didn't mention the choice of Lagrangian, so this is what I'm doing here. So if we have compressible fluid subject to rotation, you have here the kinetic energy, the contribution of the rotation of the Earth, and the internal energy. For simplicity, it's barotropic, so no entropy, but it's easy to add. And as a preparation for later, I insert here the flat operator instead of writing G of VV, because I will not discretize G, I will discretize flat. Applying the Hamilton's principle or Euler-Poincaré principles for this Lagrangian, I get these equations. So you recognize the one I had in the first slide without the gravitation, and this is an abstract form of the omega cross V term that arises from the rotation of the Earth. So systematically we can now associate it to this continuum version, the discrete version in space, and you see exactly, so rho is discretized with D, and the internal energy is simply the same function but evaluated here. So without entering in the details here, this is just a comparison between the continuum variational geometric description and the spatial discrete one. So far I have shown the discrete diffeomorphism, its Lie algebra, the various actions, and the Lagrange d'Alembert or Euler-Poincaré d'Alembert principle. I also have shown to you this principle here, and it remains to explain a little bit more concretely what happens when I specified, for example, the mesh to be 2D simplicial mesh. So this is what I will do next. So you see it's very systematic, right? So once your diffeomorphism group and your Lagrangian is chosen, you have no more choice for the equations. They emerge from the variational principle. So more concretely now we consider this kind of mesh discretization, not necessarily regular. And we interpret our A is our Lie algebra element. And here I need some notation. So given this kind of grid, F is the length of this edge, H is the length of the dual edge, so the one that relates the center of this cell, and T are the area of these triangles. I can give a discrete form interpretation to all the quantity that I mentioned so far. For example, A flat is a discrete one form on the dual mesh. So for those who are not familiar to that, the dual mesh can be associated to this in a simple way. Here I take the Voronoi dual, and it happens that our discrete velocity Aij corresponds in fact to a discrete one form on the dual mesh, not the primal one. So this is a choice for the flat operator on this kind of meshes. So there are two cases here to be considered. If the two cells are neighboring cells, your flat operator is very easy to define. You see this is given in terms of the length, the geometric length of the grid, right? H, F, etc. And for cells that are not neighboring, it's a little bit harder. You need to get inspiration from the discrete exterior calculus, but you can ultimately do this, no problem. And what you get before this is a discrete version of the Lie derivative. So if I go back here in the, I have to go back a little bit more, I think, the first slide here. This object is the main difficulty, right, when you discretize fluid dynamics, the Lie derivative of the momentum. So, and in our description, it corresponds to this term here, the Lie bracket of A and dl dA. And on this specific choice of the mesh, we get some expressions that ultimately is clearly a discretization of the Lie derivative, but really not easy to find. But this comment is just to tell you that we don't discretize the Lie derivative directly, we discretize the variational principle, and we find this as a result. So if I compare, for example, the continuum expression of the Lie derivative, this is the Lie derivative of a one-form density along a vector field U. It has three terms. This is one way of writing it, right? And you see that the discrete form really mimic the continuous one. You recognize here, for example, the vorticity at minus and at plus, which corresponds to the vorticity here and here. And here you see, for example, the discretization of dV, which is in general a hard task, which is given here. K are constants that arise from the choice of the flat operator. And similarly for the other terms. Here, for example, you recognize the gradient of this should be V flat dot U. You recognize here, this is the inner product, but with contribution from cell I and J, and doing this minus this mimics the differential operator, etc., etc. So at the end, by choosing the Lagrangian, you get these discrete equations, as I already explained, right? Where each term can be related to the continuum version of the equations. So the explicit form of these expressions is not important. It's a little bit heavy, but the message I want you to pay attention is that we don't discretize the equations themselves. We discretize the variational principle. Then we get some expressions, and we recognize that these expressions are the discrete version of some form of the equation. So the form that we have is not the usual form that in which you would start with. For example, it's not the usual form I had at the beginning of the slide. It is this form here, right? Where it is here, where the Lie derivative has been splitted in a very geometric way, these equations here, etc., etc. So now if I compare this discretization of the Lie derivative with other works, I see that this is first discrete version that hasn't been considered so far, because it makes use of, for example, if I have in this, I consider these two cells here, it considers vorticities here and here with appropriate contribution of the flux on each of these phases, right, in this order, which wouldn't be easy to guess from simply looking at the term. Also, what we recover is reminiscent for C-grid discretizations, and but it differs on ordinary ones in the fact that usually it's very hard to find such discretization in the same time as preserving the energy of the system. It's very hard, but here we can get them directly. So I have so far understood the spatial discretization. The temporal one can be discretized by standard method for discrete mechanics on Lie group, because the group the configuration space I have is a Lie group, And an important ingredient here is the discretization of this quantity here, which is q dot q minus 1, where q is in the Lie group, and this results in the Lie algebra. So there are ways to do this in a geometry preserving way. In the discrete case, this is done by using the Cayley transform, as has been devised in this work, so I will not explain this in detail, but just to ensure you that our temporal discretization is compatible with the spatial one that we did so far. So now I'm ready to show some numerical tests. These tests we have considered three main topics. First, how our scheme preserves steady solution. Yeah, we would hope that it does, right? Which it doesn't introduce spurious modes. This is another standard test that are used to evaluate schemes, the interaction of two co-rotating vortices, and if I have time, some instability test. So the first is a steady solution. So the three equations that I consider here are the shallow water equations. So these are, from a geometric point of view, they have the same variational principle as the compressible 2D Euler equations, with the difference that the mass density is replaced by the height. It's advected like a density. So the internal energy that we use here is simply 1/2 h squared. And these equations admit these steady solutions. You see here the profile of the velocity and the profile of the height. And to confront this with ordinary test, we consider several regimes, right? In each of them, so this R is the Rossby number. It tells me how the stratification is important in my problem. This B is the Berger numbers. It tells me, no, the Berger numbers tell me how the stratification is important, and the Rossby how the rotation is important. So if B is very large, we are close to the incompressible fluid. We know that this has already been done, so this has to behave nicely. Important for us is this regime, in which the contribution of the compressible character is important. Okay. So we choose irregular mesh discretization, and we inserted these initial conditions, right? It's a steady vortex, and we hope it doesn't move. That's the hope that we have, because it has to be preserved, because it is preserved by the continuous equations. So, and the result is good, right? After 100 days, it hasn't moved too much. It hasn't deformed a little bit, but after 100 days only. And also, you have to remember that this is an irregular mesh discretization, right? So we also observe that there is no spurious waves that are emitted from this, which is good news. This test also allows us to estimate the convergence of our scheme. We didn't do any analytic convergence, only the numerical one. And as it should, it's between first and second order, both in the L2 and in the L infinity norms. So here we choose to estimate the depth, right, and the relative potential vorticity. You note here, for example, that it's for the depth, it's even better on irregular mesh, because by chance our mesh has smaller cells exactly where interesting things happen. So here, this is the explanation why it's better on irregular grid, but for the other quantity it is not. This is a standard test, the interaction of two vortices. So this has been well documented, and so it agrees well with the literature. Here we have, for example, in the first row, the result on regular meshes. Here we have on irregular ones. And I can show some numerical simulation that we did on these interactions. This is this one. So initially, the vortices are in geostrophic balance, right? And they should still move because they are not they are solution of the linear equation, but not the nonlinear one. So they should evolve, and what we see that we compare the velocity of the rotation and the distance. It agrees well with well documented test case for this situation, right? And we also, of course, examine the energy conservation, so it's doing well, right? Both on regular and irregular grid. And to finish, I would like to mention that our scheme is not meant to preserve Casimirs, right? We didn't impose preservation of Casimir in our problem, because we discretize a Hamilton system using non-holonomic mechanics. So we lose a little bit the Hamiltonian character. But nevertheless, these Casimirs are well preserved, not as well as the energy, but they are well preserved. For example, the Casimir in this case is the potential vorticity, and you see that it's doing quite well. Okay, so let me conclude. So I presented a variational discretization for compressible fluid dynamics. My main interest is GFD, so I consider the shallow water equations, but other models should work the same. The main interesting aspect that is that it provides discretization on irregular meshes, which is important for the sphere, for example, or the fluid on other manifolds, or if you want to do some refinement. We can do both 2D and 3D, regular, Cartesian, or simplicial. So this is extremely an initial step, right? There are many directions in which we hope to make some contributions. For example, to go to higher order, right? It's very extremely low order what we have, but it's technically possible to do higher order, and also to have a deeper explanation of this Casimir conservation that we don't really understand so far. And of course, for many of you, how can we use such discrete version of dynamics on diffeomorphism group, for example, for shape analysis or computational anatomy, etc. Right? So thank you very much.
So many thanks. Questions?
So my question is with this variational structure, because for me the underlying idea of variational integrators is you replace a variational principle on continuous paths with a variational principle on a discrete path, or something like that. But here, when you add these non-holonomic constraints, you take away the variational structure of your equations, right?
No, in some sense, I have to include the constraint that appears in my description, but I include them in a physical way, right? I use the physically correct variational approach for this. Right. The Lagrange-d'Alembert principle.
Yeah, but you don't. But in the end, the equations you're solving are not from a variational principle, then.
They are from Lagrange-d'Alembert principle.
Right, but yeah, which is not variational.
Which is not delta something
right.
E0, it's delta something E0 for some kind of variation.
Yeah, but I guess this is also related to what you say. So this is the reason that you don't have the Hamiltonian structure.
This is exactly the reason.
Yeah. I mean, there's very good numerical results, so that indicates that it somehow still works out.
Yeah.
The other question I have is, one way to look at this is that it's a Hamiltonian system on T star diff compressible. And if your underlying manifold M is some domain in Rn or something like that, then essentially T star diff is going to be an open subset of a vector space. So in that case, you could say, well, it's just a Hamiltonian system on the cotangent bundle of a vector space. So we have many, methods for that, symplectic integrators and so on. Of course, I'm not now talking about time discretization, not spatial discretization. So, do you think that could be another approach, or have people done this already?
It hasn't been done, for sure. This is clear. But are you saying that the diff of a domain D with boundary is the open subset?
It's an open subset in a large vector space. In that case, you can just apply normal symplectic integrators. And it's even nice because the Hamiltonian is separable, so you can use Sturmer-Fallé or something like that. You get sort of explicit schemes.
Wouldn't it be hard to preserve the symmetries in this case when you extend so far?
Maybe. I mean, at least I'm just thinking about simplicity. I'm not thinking about symmetry. Yeah, maybe you're right.
Okay, are there more questions? Please.
I have a question about the numerical dispersion of your scheme. How would you evaluate the numerical dispersion? And do you have any suggestions of how to counteract it?
So we are trying to mix this with upwind techniques, but it seems to be extremely hard to preserve at the same time these Lagrangian properties and the variational structure that we are doing here. But this is also due to the fact that we didn't tune in any way our transport equations. We simply take the easiest one that comes from our schemes, right? So it may be possible to have a better scheme for the transport equation, but without altering the good properties of the first one. That's the main difficulty. But it is dispersive in this case, yeah. Also, we are trying to evaluate how it does with shocks, right? So, shocks velocity seems to be okay, but of course we have deformation.
More questions? So maybe I have a question. So you also encode gravity.
Yeah.
What about the moon and its actions on the atmosphere?
Ah, okay.
Tides or atmospheric tides?
Yeah. Yeah, it can be included in the formulation. I don't think that this is a major problem. Yeah.
Okay. More questions? So that was the end of the afternoon session, and now I think there is a welcome wine.